So, good morning, evening, or day, everyone. So I think we'll start right away so we can have enough time for all presenters. I'm Jelena Gabela, and I will be hosting this webinar today for you. I have a background in geodesy, so I'm well interested in this topic. I originally got my bachelor and master's degree in geodesy and geoinformation in Croatia, and then I went on to do my PhD at the University of Melbourne in Australia. At the moment, I am at the Vienna University of Technology in the Engineering Geodesy group. So I want to thank you for joining us for today's webinar, Advancing Geodesy and Navigation with Quantum Sensors, which is presented by the International Association of Geodesy, Project QuGe, Novel Sensors and Quantum Technology for Geodesy, Joint Study Group 411, evaluating the potential of next-generation quantum sensors for positioning, navigation, and timing, and International Federation of Surveyors Working Group 57, about emerging technologies for PNT, which is co-chaired by myself and Professor Alison Keeley. And of course, not to forget, Innovative Planet Institute, Swinburne University of Technology. So quantum sensors are revolutionizing the world by providing unprecedented precision and sensitivity in measurements. These sensors leverage the principles of quantum mechanics in order to detect minute changes in physical quantities such as time, magnetic fields, gravitational forces, and so on. And this technology is basically enhancing capabilities in wide range of applications, from improving medical imaging all the way to environmental monitoring. The impact of quantum sensors also extends to critical areas such as national security. So, for example, they enable more accurate detection of threats, and also in industry, where they contribute to the development of next generation technologies. Today, we will delve into quantum sensors and their role in geodesy and navigation. So we will hear from 4 speakers, and after we hear from them first, we will have a Q&A session in the last 30 minutes. So our 4 speakers, first one of which is Paul Wigley. Paul is a co-founder and the COO of Nomad Atomics. Nomad specializes in the design, manufacture, and deployment of next-generation high-precision quantum sensors. Their survey-style absolute quantum gravimeter is aimed at providing a step change over current gravimeters, offering high-precision, drift-free measurements of absolute gravity. Paul holds a PhD from the Australian National University, focusing on techniques for making atomic sensors smaller and more efficient. Our second speaker is Professor Jürgen Miller. He's a full professor in physical geodesy at the Leibniz Universität Hanover, Germany, since 2001. He studied geodesy at the Technical University of Munich, where he also finished his doctoral degree in 1991. With excellence, and his habilitation in 2001. His main research field covers gravity field satellite missions, terrestrial gravimetry, including novel measurement concepts, related Earth system research, lunar laser ranging, and general relativity. In the past years, he focused his research on elaborating the potential benefit of quantum technologies for geodetic applications. Examples are quantum accelerometers, gravimeters for ground and space use, as well as optical clock networks for novel height systems and monitoring of mass variations. This research has been carried out in large collaboration programs together with physicists like the DFG CRC 1464 TerraQ, of which Jürgen Miller is the speaker. This new research field has also been pushed by the International Association of Geodesy by establishing the major project Novel Sensors and Quantum Technology for Geodesy, QuGe, with Jürgen Miller as the chair. Our third speaker is Keshav Tirumalai. Keshav is the inertial sensing lead of Inflection UK. He holds a PhD in atomic and laser physics. from the University of Oxford, UK. He has spent the last 4 years at Inflection and in collaboration with BAE Systems and QinetiQ, completed the world first flight trials for quantum navigation technologies in UK in May 2024, so just recently. Last but not least, we have Professor Alison Keeley. Alison is the inaugural director of the Innovative Planet Institute at Swinburne University of Technology, Australia. Prior to this, she was the executive director of the Surveying and Spatial in the Department of Transport and Planning. Alison has also held academic positions at the RMIT University and the University of Melbourne, Australia. She holds an undergraduate degree in land surveying from the University of West Indies in Trinidad and a PhD in GPS and Geodesy from the University of Newcastle upon Tyne, UK. Alison's research interests include quantum PNT, sensor fusion, Kalman filtering, and estimation theory, high precision satellite positioning, GNSS quality control, wireless sensor networks, and location-based services. Alison is a fellow of both the Royal Institute of Navigation and the International Association of Geodesy. So, of course, even during the talks, we invite you to write comments or any questions in a Q&A box that you have on your screen. Please also write who the comment or the question is directed to. We will then in the Q&A session read these comments, not during the presentations. And at this point, I would love to hand over to Paul Wigley for the first presentation. So Paul, over to you.
Thanks for that introduction, Yelena, and yeah, nice to be here. Can everyone see my screen and camera?
Yes.
Perfect. So yeah, as Yelena mentioned, my name is Paul Wigley, and I'm a co-founder of Nomad Atomics. So briefly, I would like to introduce Nomad and talk about some of the things that we do. In a nutshell, we focus on the development and deployment of quantum gravimeters and accelerometers. We've brought together a technical team with deep expertise in these fields, with our team having been part of projects working on developing high-precision BEC gravimeters, developing simultaneous multi-field sensors of magnetics and accelerations, as well as deploying the highest accuracy transportable quantum gravimeter in Germany. So we've taken all that expertise and focused heavily on full stack hardware development to build unique fit for purpose tools designed from day one to meet the capability and size, weight, and power requirements needed for the resource and navigation sectors. So Nomad at its core is a vertically integrated technology company. So we don't just focus on the quantum sensor hardware itself, but we provide field data acquisition services, gravity map analytics, and inversion analytics for dynamic underground systems. That said, all of this is underpinned by our next generation quantum sensors designed and developed in-house. But what are quantum sensors and how do they work? Well, let's start with the very basics and work our way up. The basic operating principle for all quantum sensors is essentially the same. It requires only two main elements, light and atoms. We use light to store some known information onto our atomic state. We then let these atoms interact with some element of the environment, say gravity. As the atoms interact with this external field, the information stored on those atoms is changed ever so slightly. This change is then read out from the atoms using light once more, with the result telling us critical information about our environment. Depending on the type of information and how it is stored, we can probe different characteristics of the environment to very high precision. This can be anything from magnetic fields, electromagnetic fields, gravity, accelerations, and time. To go a little bit deeper, let's look at how cold atom inertial sensors work. In this case, we have an accelerometer measuring vertical accelerations. We begin by using light and magnetic fields to trap and cool a cloud of atoms in a vacuum chamber. Importantly, the cloud is cooled to the point where it can be released and be in free fall for tens to hundreds of milliseconds before dissipating. Really, the colder the better here. And for context, we're talking about temperatures that are a millionth of a degree above absolute zero. And once released into freefall, the atoms are manipulated through a series of 3 interactions with an optical lattice. This lattice is generated using a vertical laser beam reflected back on itself with a mirror. And this mirror here is our inertial reference. And a nice analogy is that these 3 interactions are similar to measuring the free fall of a classical test mass at 3 points in time to determine acceleration. There's obviously a little bit more to it than that, but this provides a nice little analogy to think about. Now, in this case, the interactions of the light and atoms form what's called an atom interferometer, whose phase is directly related to the free fall acceleration that the atoms experience. Finally, this atom interferometer output phase is detected optically, producing a direct measurement of that acceleration. Going even deeper, this is roughly what it looks like. I won't go into the precise detail here since we only have a short amount of time, but I do want to emphasize the key point, which is that the measurement, in this case, acceleration or gravity, can be traced back to laser wavelength and sweep rate, both of which can be known to very high accuracy. The precision and the dynamic range of the measurement can then be tailored by simply changing the time between these 3 pulses. Importantly, it allows us to relate everything we measure back to fundamental, unchanging properties of the atoms, instead of some mechanical artifact that might be changed by many variables. What really counts here, though, is that quantum sensing in general combines a unique set of characteristics that have not been seen in previous technology. First, it allows these sensors to be integrated into small, lightweight packages with no moving parts. It also means they have world-leading accuracy and stability and can detect even the most minute changes in the environment around them. When you put these traits together, this enables quantum sensors to really enhance existing applications and even unlock totally new ones. So to contextualize this a little bit, I would like to briefly touch on classical gravity sensors to really highlight the benefits that quantum sensors provide. We've really been using the same technology for gravity sensing for many decades now. Land gravity has been dominated by the Syntrex CG systems. And while absolute gravimeters like the FG5 and A10 exist, they're used rather sparingly due to the difficulty in deployment, both in their size and fragility. And similarly, airborne systems for gravity and gravity gradiometry have arguably not changed from the CMG and tensor systems. All of these gravity sensors rely in one way or another on mechanical measurement systems or mechanical modes of operation, and each suffer from one or more restrictive property. In the case of relative devices, this is drift susceptibility or shock susceptibility, bias or tearing. And on the absolute side, it is large infrastructure overheads or size, weight, and power limitations, or even just simply the expense of it. And these technical limitations lead to real world limitations in the form of data fidelity or deployment and survey costs. In contrast, quantum gravimeters combine the positive aspects of existing absolute gravimeters, that being absolute accuracy, stability, and sensitivity, combined with the benefits of current relative sensors, being truly field deployable and with a pathway for even further miniaturization. I'd just like to draw your attention to the data on the right side here, which formed part of my other co-founder, Christian Fryer's PhD, where he built a transportable quantum gravimeter and performed a series of comparisons at different locations across Europe. The top plot shows a gravity measurement with tidal variations over the course of about a week. The middle shows the residual after the subtraction of those tides and shows a small signal from hydrological and atmospheric disturbances. The bottom shows a comparison to a co-located superconducting gravimeter and shows excellent agreement. So quantum gravimeters have demonstrated world-class performance, showing sensitivity down to 9 × 10⁻⁹ G per root hertz, accuracies down to 4 × 10⁻⁹ G, and world record stability down to 4 × 10⁻11 G. In addition to that, this campaign really showed important practical advantages for gravimetry over conventional commercially available sensors. So quantum sensors exhibit world-class data quality. Why haven't they made it to widespread use yet? Well, there have been and are many challenges to bringing a device like this to market. The device my co-founder built for his PhD still required transportation in a truck and long setup times once at location. Importantly, though, the challenge has now moved from one of physics to one of engineering and integrating these sensors down to a size where they can be useful. There is great challenge in these engineering problems, but much progress has been made globally to improve a lot of the peripheral technology required for this miniaturization. Also important is the applications that these devices are initially built for, which potentially allow for some trade-off between the key attributes. And most commonly, this is between size, weight, and power, and the sensitivity. So at Nomad Atomics, we've spent the last few years customizing, miniaturizing, and integrating all the major subsystems that go into a quantum sensor, from laser systems and vacuum systems to power and control electronics to optical distribution systems and many more. The quantum gravimeter that Nomad has developed, called Absolute G, is the culmination of all this foundational work. We've really leveraged the quantum advantages I mentioned earlier by pushing the integration and size far beyond what's available today. Absolute G, excuse me, Absolute G is a truly portable device built for field surveys while maintaining the accuracy and stability exemplified by quantum sensors. So with a sensor that is now 90% custom, we've been able to push the integration and form factor into a device that can be easily taken out into the world and used, unlocking a whole range of applications. What does this mean, the introduction of a compact absolute gravimeter? Well, at a minimum, it means that we now have a tool to cost effectively and efficiently maintain, build, and even expand large-scale absolute gravity networks, providing more and more reliable tie points for gravity surveys. One step further, and they can be used directly to provide high-fidelity land exploration maps without that need for tie points, and with the added bonus of intrinsically level gravity surveys. This means that you could directly compare every map taken, no matter the place or time. As systems become more integrated, the size will allow for gravimeters to be moved via drones, reducing personnel overhead and increasing that measurement capacity. As the technology continues to be integrated, there's a real pathway, which we've already started development towards, to a octocopter drone vector gravity and gradiometer. All pretty exciting stuff. So in the future, there are clear applications for quantum accelerometers and gravimeters, from navigation to time-lapse measurements. In the navigation space, the stability of these sensors can improve the potential duration of navigation without external conditioning, such as GPS. I think Alison will talk more about this later. In exploration and mapping, quantum absolute gravimeters will enable much more cost-effective regional and continent-scale gravity networks, or even simply mapping using absolute devices, ensuring that gravity maps are inherently level and comparable. In monitoring, the ensured accuracy will allow changing gravity signals to be monitored over months to years to allow for the direct measurement of the movement of mass underground and the deployment of true time-lapse gravity. There's huge potential here, and we're only really just scratching the surface. I think Keshav from Inflection will talk more about all of this shortly, so I will leave it here, but thank you very much for your time.
Okay, then I will move on and give you a flavor on how we can use this new technology for geodesy, not only in gravimetry, but beyond this, going to space and also using clocks. So my name is Jürgen Müller. I have nicely been introduced, and now let's see what my understanding of geodesy is and how we can use it. So our goal is to determine physical heights, as well as the height reference surface, a geoid or quasi-geoid, so zero height. And as a reminder for height systems, worldwide we have about 100 different height systems, which are off by decimeters, centimeters, decimeters up to meters. So somehow we have to unify them. Another major application is observing, monitoring mass changes related to groundwater and precipitation, but also due to ice melting or sea level rise. So quantum gravimetry already has been addressed.
Jürgen, are you advancing your slides? Because you just put it into presentation mode, because I don't think the slides are moving for us.
Is it now in presentation mode?
No, I don't think so. No, not yet. So down at the bottom.
So, but in my case, I did it as the same as before.
Yeah.
So what do you see?
I see a slide with quantum gravimetry now.
Yes, and now I go to full screen, and now? What do you see now?
No, I don't see you going to full screen.
So I don't know. Before it worked before, so can you give me a hint what to do?
Did you share your screen?
He's sharing the window.
Or the window?
Oh yeah. So should I share the screen?
Yeah, share the screen, please.
May I go back?
Yeah.
And let me see. So share the window.
Share this. Yeah.
Do you see anything? No.
No. Have you shared the screen?
Yeah, I tried, but it does not open it, the screen. Maybe now? Can you see anything?
Yes, now it's fine. Yeah, great work. Thanks.
Maybe I should go back. So what I introduced before, that we are interested to observe height systems, so height systems as well as geoids, so high physical heights and mass changes. As I already mentioned, ice mass loss, sea level rise, and also due to groundwater variations. And now I stopped when I wanted to continue what we have heard before by Paul, quantum gravimetry. So the difference to classical gravimetry is that in the classical systems, we have falling corner cubes and do time and distance measurements. Now we have falling atoms, as you see it here in this sketch, where the motion of atoms is in an interferometer case is related to little g. You already seen this one, that indeed the atoms are split by light and manipulated by light and then excited half of it and recombined after time 2t. And the observed phase shift is then providing the little g value. And here you see it once again, how it is symbolized with the main contributions. And here in Hanover, we have such a system as it has generally explained by Paul. So what we also have in Hanover is not only a small one with 1 meter size or even smaller, but we have a tube with 10 meter fall length. And this means this can achieve an extreme high accuracy, which will provide a new gravity reference, so that in future you can even calibrate or validate all gravity sensors along such a device. But more interesting for field exploitation are transportable ones. And the advantage already introduces the high accuracy within short time, so that we can do new, faster surveys, but we can also use it as a registration device, as it has been shown before. And the goal is to really miniaturize it and to make it easy handleable. So it's an engineering technique, more or less. Applications are shown here. I just give 3 examples. One with a combination of one and other gravimeter in Germany. And over the years, one see droughts and precipitation change in the signal on ground, in groundwater and on the surface. And over the years, these are 5 years, we see on water loss, groundwater loss in this German site registered by such an gravimeter. Another example is given by the Italian and French colleagues. This is monitoring Mount Etna volcanoes, and the upper curve on the left-hand side in P is a one gravimeter, the other one is an iGraph, another gravimeter, and on the bottom you see possible over the year's mass, over the month's mass changes, and they are well recorded, a little bit more noisy in the one device at that time, but this will improve. So you can nicely capture these effects. And one of these effects is, for example, if you have cracks in the volcanoes, it's filled by magmas, and you can clearly see it as it's shown here in the example, see between location 1 and 2. Now, as I already said, you can not only use it on ground, but also in space. In space, gravimeters are used inside satellites to observe non-gravitational accelerations, for example, in graceful on. Or you also use an ensemble of accelerometers, like in the QuGe case, to run gradiometry. And you have also more complex constellations, which I will give you a few examples how far we get in these situations. So here on the left-hand side, you see a figure, the frequency, and then the error curves of various accelerometers. The superstar is what is used right now, and these are electrostatic as well as the other colored curves. And you have this huge drift at the lower frequencies, even in, on novel ideas. And the cold atom interferometric accelerometer can achieve white noise to a high level. And if you want to use it in space mission like GRACE, then the main instrument is not only the observation of the non-gravitational accelerations, but it has to be combined with the distance measurements, and these are the same range, acceleration range. It is combined with laser ranging interferometry in the satellite tracking, and you can see somewhere maybe the cold atom interferometer can even supersede the LRI measurement. So both have to improve in the satellite tracking as well as the QuGe accelerometry. And we can also, and what we are expecting in the future is that we'll have a combination, hybridization of electrostatic and QuGe instrument. And this looks like this. So where you can benefit from advantages of all the systems, because then you have you can achieve a wide noise behavior over all frequencies which are relevant. And here now my example started together with colleagues from Munich. The most upper curve is what we have right now in a GRACE mission, polar mission, and here the other colors show different hybrid instruments, QuGe plus electrostatic, and you can see that you can certainly supersede all the electrostatic measurements in this case, in the ideal case, by order of magnitude. But this is just theoretically, because we should not forget that one major issue in the space missions is temporalizing, so high frequency mass variations. And if you switch them on, then you see that you can now you add it to the accelerometer and LLI errors, also the model errors, and then it goes roughly up. And only if you can improve these models, you see, to 10% error, then you can really benefit from the electrostatic accelerometers. On the right-hand side, a situation is on the left-hand side from a GRACE-like polar pair. On the right-hand side, what is right now prepared is a Bender constellation, 2 pairs of satellites. Then it's a little bit better, but even here, it is that you should improve this background modeling, hydrology, and atmospheric ocean mass variations, that you can fully exploit it. So temporalizing is a major problem, not really the sensors in space. What we also did is we run a simulation. If you do it, if you apply this hybrid accelerometers for gradiometry, and then we could nicely show that the spatial resolution, so that you can on Earth, that you can get finer resolution of the gravity field on Earth, that it can be improved largely if you apply this, if you include QuGe sensors, so quantum sensors, and then even the best case, you may be able to use gradiometry to determine time variable gravity field contributions, which is not possible right now. So we'll see. This is another future concept. Now, the last part is on using clocks. Atomic optical clocks also are quantum sensors, and we can I will show you how we can use it in geodetic application. What we exploit is what we know from Einstein. Then clocks tick differently if they are on different locations in the Earth's gravity field, and then the frequency, the relative frequency, so-called redshift, as observed as frequency shift, is directly related to potential differences. So you see potential differences, for example, between potential on the geoid and when the clock is on the geoid, and one is above. So you can observe this frequency difference, which is directly related to the potential difference. And this is what we use. This is what we use in our physical heights, for thinking orthometric heights. We use this potential difference, and maybe in future, and we obtain it by leveling and gravity measurements, but in future we can directly use these clock observations. And today, clocks have achieved an accuracy, or achieving an accuracy of 10⁻18. That means we can resolve height changes of 1 centimeter. And if you add maybe GPS or GNSS measurements in the clock locations, then we can also point-wisely determine the geoid or quasi-geoid. And this is really chronometric leveling as we can use it. And how we can use it, we already mentioned these differences in the height systems. So we made simulation, because right now we do not have so many transportable clocks. We did simulations, here an example in Europe, where we introduced artificially offsets, tilts, problems at leveling lines, so that we had in the beginning between 4 different height systems, 40 centimeter up to 40 centimeter errors, differences, and with a few clock measurements, that means 4 or 5 in sub areas, we could resolve all these issues and could get down to the centimeter level. So we can really detect discrepancies and distortions, leveling lines with those systems. Then we extended it also to connecting remote areas. So we did the same, for example, in the Brazilian system. We used Brazilian data, but then simulated clock measurements with all these error sources, which are symbolized at top. But now we also have to consider that we have to connect these height systems. So normally optical clocks are connected by fiber links on ground to achieve the highest accuracy. So here we need space links, free space links, and there we have to make assumptions how well the links are, how well the clocks run. But even there we can show, and also modeling errors, that we can connect those remote areas and unify even these height systems over continental scales, if the clocks and links are sufficiently accurate. Then I already showed you this redshift formula, and you should keep in mind that as the clocks are resting on ground, they not only observe height changes, but also mass changes. So this delta W consists of 2 parts. And for example, to give an example on height changes due to tidal effects. So this is the German Meteorology Institute, PDB in Braunschweig. And there we have changes in the decimeter level, which means in clock accuracy is 10⁻17, a few times 10⁻17, and with a clock accuracy of 10⁻18, this can well be captured. So that means you have to model this, and then you can get also information on the mass changes. And here, my colleague Asher Vincent ran various simulations. If you look at the figures on left-hand side, we see first the colors in the first figure is always the difference between mass variations and GNSS-based height variations. And clocks see all together. So we see these periodic variations, seasonal effects due to the monsoon times in the Himalaya region, even higher in the Amazon region, and you see dominantly these periodic variations. On the left-hand side, on the bottom, you see trend signals. Let's look at Greenland, and say you see height variations due to the elastic response after ice melting, but you also see the mass change, and clock sees both. So that means with clock measurements, we have additional information on the ongoing process, and the advantage is you have a much higher sampling rates. You get this result, one point value within one day or 2 days. In grace, it would be 1 month. And so you can do a different kind of observation. So final example, just clocks in space. We use the same formulas, this timing formula again, but now do not combine velocity and potential part. We are now interested in observing gravitational difference between the ground and the space clock. We have to get rid of the velocity part. If you just want this potential, we have to take care on the links. But in ideal case, and just this is one example, you can use clock measurements to observe, for example, the change in flattening. The flattening. So here you see periodic changes, which is now observed with SLR and provided to the grace case. My final figure is this one, which compares in space various technology. So on one hand, you can see that chi-based radiometry can really supersede by 1 order of magnitude the QuGe case, so get a higher spatial resolution. We can also see that at the low frequencies, grace, as a low degrees, grace is superior, and there it can even more benefit if we include some cold atom interferometric accelerometer. The clocks maybe only at the very least low frequencies. That means maybe to observe the flattening parameter. So let me summarize these applications. So we can have we can apply those quantum gravimeters in space as accelerometers. We can use it on ground for monitoring more local and regional mass changes. We can explore relativistic geodesy for height systems, also for giving a global reference, and for monitoring mass variations. And on the bottom, you see we have these projects on the international level, QuGe, and on the national level in Germany, this TerraQ, which has been mentioned in the beginning. And if you want to contribute to one or the other, please contact me. Now I'll stop and hand over.
Great. Thank you, Jürgen. Thanks very much for that really nice talk. And thanks, Paul, before. Yeah, my name is Keshav Thirumalai. I am the inertial sensing lead of Inflection UK, and my background is a PhD in ion trap quantum computing, actually. So I thought I would just briefly talk about the flight trials we did as part of activities at Inflection, but I'll start with just an introduction of who we are. So Inflection are a quantum platform company working with cold atoms, lasers, vacuum systems, and we have products and prototype products in a whole variety of different areas, from clocks, inertial sensors, quantum RF, all the way to quantum computing. So today we're talking about quantum inertial, but we span sort of all of these, and we are based headquarters in the US, but we have a significant presence in the UK and in Australia and now in Japan. So I won't labor the point too much, but I think all appreciate that position, navigation, and timing is absolutely crucial for modern society to function, and the variety of applications are on the screen. A nice stat that I like to give was there was a report in the UK a few years ago showing that a GPS outage in the UK would cost the UK economy £1 billion a day, and I'm sure similarly large numbers would be reflected around the world. So our reliance on GNSS and GPS in particular is really a critical risk to global supply chains and critical infrastructure and really everything. And lately, with the conflict in Ukraine. We've seen a lot of examples of active spoofing and jamming, and regularly flights in that part of the world and nearby see situations where they cannot rely on their GPS signals to fly, and obviously they have redundancy and backup, but this places significant constraints on what and how they can operate. And so there's really a need for resilient position navigation and timing that doesn't rely on the receipts of external signals, which can be hacked and spoofed and jammed and so on. So essentially, over the last 10, 20 years or so, we've seen lab-based cold atom inertial, cold atom interferometric sensors really push the performance limits of inertial sensors in general. So they can achieve really low bias stabilities and really low noise figures, and these compare really favorably against many of the inertial sensors that are used for navigation today. I actually skipped explaining how inertial navigation works. I'll just briefly explain that if you, instead of navigating with a reference from satellite positioning, you start with a known position. You then integrate forwards your acceleration and your rotations for the period of minutes or hours or even days, and you can know your position going forwards, but the growing errors of classical sensors mean that your uncertainty of your position grows and grows exponentially to the point where it becomes useless. And so that holdover period, how long you can navigate while you are denied GPS, whether that be from an adversarial factor like I described earlier, like in a conflict, or even, for example, when you're underwater where you don't get GPS at all. These the limitations of current sensing places limits of how long you can navigate in a safe and reliable manner. Also on timekeeping, which I won't really talk about today, quantum optical atomic clocks have shown really fantastic performance, and actually can beat the general trade-off between size, weight, performance, and size, weight, and power and cost and performance. And so that's a product that we're working on, but I won't cover today. So Paul already introduced very nicely a lot of detail about how quantum inertial sensors work, and the gravimeters that he's working on are very similar in function and style to the accelerometers and gyroscopes that we work on. So I won't go into loads of detail, and that was covered really nicely. Thank you, Paul. But essentially, we take a vacuum chamber. We take our population of, in this case, rubidium atoms, and we cool them down with laser beams. And we cool them down all the way with a process called evaporative cooling, where we forcibly remove the hottest atoms down to a Bose-Einstein condensate, which is the coldest state of matter in the universe. And with that Bose-Einstein condensate, we conduct interferometry. And for the case of rotation measurements, this is very similar to how current state-of-the-art classical gyroscopes work. And an example of that is in the bottom right, which is a interferometric fiber optic gyroscope. So you take light, you split it such that you send the same laser beam down opposite directions of an optical fiber. And you measure on the output the interference pattern, and you can say something about the rotation rate you've experienced during that period. So we do the same thing with atoms here. We split them, we move them through opposite directions in a loop, and they enclose an area. So this is called Sagnac interferometry. And on the output, we look at the interference pattern and the relative populations in different momentum states, and you can know something about the phase you've acquired through acceleration and rotation. One of the important things here is that the temperature of the atoms has a lot to do with the quality of the interference output. So in the same way that light interferometry is, you have far higher contrast with laser light interferometry as opposed to white light interferometry. Interferometry with a Bose-Einstein condensate, you get a lot higher contrast than you do with a thermal collection of atoms, because the temperature of the atoms directly relates to their wavelength. So having all the atoms in a Bose-Einstein condensate means that they're all at the same velocity, they're all occupying the same macroscopic quantum state, and so the wavelength of the matter waves that interfere is the same, and it's in phase, and you get this really nice high contrast measure of your acceleration and rotation. So I wanted to talk about what we've done recently and achieved in Inflection, which has been some really nice results. So we are at the proof of concept stage in terms of taking these systems out of the lab and into the real world environment. And I mentioned that there's been some lovely results in the lab, but this is these sorts of sensors coming out into the real world are just sort of emerging. So in May this year, we did a series of flight trials over 3 months, working with our partners, Kinetic and BAE Systems, to put systems like this in an aircraft. And so this was an RJ-100 aircraft. It's a jet aircraft, a fairly large one, where the inside has been kitted out for sort of experiments and testing of both civilian and military hardware. So during these flight trials, we tested our inertial sensing platform and our optical atomic clock. And I'm really proud to say that we achieved a few world firsts. So we achieved the first ever in-flight operation of a Bose-Einstein condensate. So this has been done before in many labs around the world. This has been even done in the International Space Station using some of our hardware, but it's never been done in this sort of dynamic environment with the engines producing a significant amount of vibration and the sort of general harsh and noisy environment you get while flying around. And similarly, we had the first in-flight operation of an optical atomic clock, which was a really nice result. So just a bit more detail on what this took to get here. So this was a 3-year project funded by the UK government, working with a variety of partners, which you can see on the right. And these are laser system companies, electronics companies, and of course, BAE Systems and Kinetic, who are sort of the end users who can really understand what it takes to put something in that sort of environment. So I mentioned vibration was a significant worry for us because our system was at the back of the aircraft, not far from the engines at the front, and that's placed a significant challenge for us. During taxi and takeoff is the sort of harshest vibration as you're thundering up the runway, but in level flight the vibrations come down. So during the course of building our system up for these flight trials, we took one of our cold atom systems, as you can see on the right hand side, to a test house and subjected it to a series of controlled vibrations. And so here's a little video showing you how the system is damped on some rubber isolation. The system is spread across 2 racks here on the aircraft, but that's for sort of aircraft weight distribution. In reality, the whole system can be combined into a single rack, as you can see in the cartoon here. And it's worth saying that this is not yet a product, as you can clearly see. So maybe we're further away than Nomad are in their particular technology. But this is really a massive step change on what's been done before. So dealing with the vibrations I mentioned, but also, for example, dealing with the changing magnetic field as there's local magnetic fields created inside the aircraft, and as the aircraft flies around, the Earth's magnetic field changes dynamically. Dealing with the radio frequency environment, so you have the pilot speaking on to air traffic control. You have a really large weather radar at the front of the aircraft at a few gigahertz, blasting out watts of power, and you have a generally complex environment you need to manage and you need to deal with. And so our system of, it's essentially a sensor head, it's a set of control electronics, and its laser systems are all kind of were designed to work with this environment, and we underwent testing to get here. I wanted to show, maybe slightly tongue-in-cheek, a picture of my old research lab. So this is a similar lab working on not the same technology, but just to give you an example of where this technology has come from. So this is a sort of slightly mad picture of vacuum chambers made of steel, light delivery optics, fiber optics, electrical cabling, laser beams flying everywhere. And so this is where quantum technology is often found, and it is a real challenge to take this sort of system, which is highly flexible and adaptable for understanding and developing the physics, taking the system and engineering it into a package that can survive flight and survive takeoff and landing repeatedly was really a very significant hurdle that we had to overcome. So I spoke about one of the major challenges to taking this technology into the real world, and that was just showing that it can operate and be rugged in this environment. Another important thing to talk about here is that there are lots of different ways to manipulate the cold atoms. So on the screen here, I've surveyed a few different techniques. On the left are free space interferometers, where the atoms are free to move and they're interrogated by laser beams as they move. Where on the right-hand side, the atoms are constrained inside optical potentials. And that gives you a lot of control of their motion, but it can be more complex. So there are lots of organizations developing these technologies and putting them in deployment, and many of them are picking a certain few of these or individual to work on, and they will tell you that their particular method is the one that will win out. But I think it's worth being honest and saying that at this point in the field, it's not clear which of these techniques is actually best suited for each application. So if you're looking for an inertial sensor to operate on an aircraft, or an inertial sensor to operate on a ship or on the ground, different modalities of operating and working with the cold atoms will be needed. And the nice thing about the platform that we demonstrated during the flight trials was that the core underlying technology, the hardware that we developed, the robustness, and the processes that we developed are applicable to all of these. And so we are working on all of these during in the company during the coming months and years. And I specifically wanted to call out the top left, which is our sort of next generation system, which is a continuous beam system. So most cold atom inertial sensors operate in a pulse manner. So you prepare your atom sample, you manipulate it, and you make a measurement, and you get a measurement out. And these operate on the sort of hertz sort of time frame, 1 hertz or a few hertz time frame. And this can be absolutely perfect for fairly static applications, but for dynamic applications like navigating ships or navigating aircraft, you may need a higher bandwidth to make a meaningful improvements to current classical sensors. And so we're working on a continuous beam system here, where the atom beam instead of being cooled to a BEC is a cold thermal beam that moves through our system. And so the atoms move through light fields, receiving laser pulses as they move through the field. And we can, with this sort of system, achieve bandwidths of the order of a few hundred hertz, which when hybridized with classical sensors will be a lot more robust to providing robust navigation in a dynamic environment. The other sort of that was the second sort of challenge that exists for commercializing this technology and making this into a product. And the last one I would say is the taking our quantum inertial sensor and making it into a navigation system, because that's really what the customer wants to buy. So while a quantum inertial sensor is interesting in its own right, people interested in inertial navigation for defense applications or commercial applications really want to see their navigation system have an enhanced capability. And so what we need to do is to understand how we hybridize and hybridize these systems into a full navigation solution. So with the current limitations of quantum systems, we believe that inevitably they will have to be hybridized with classical sensors, and we heard about that in the 2 previous talks. So you combine the best advantages of the maybe long-term low drift capabilities of a quantum sensor with a higher bandwidth of a classical sensor, and that low-level integration then that is combined with a mid-layer here of sensor fusion and Kalman filtering, which we'll hear a lot more from Professor Allison. And that process of what parameters of the quantum sensor have a material impact on the navigation solution is, I think, really important, and something that is not particularly well understood. Is it worth focusing on the bandwidth or the noise performance or the drift, and how do those impact on how long you can have GNSS holdover? That's really the key question. And the last slide I wanted to show today was just on the sort of future roadmap of where this technology is going. So the system I showed previously was rather large, and yes, we've managed to take it out of the lab and have this work in an aircraft, but we need to make this smaller and cheaper. And so there are kind of 3 core areas where this technology is being miniaturized and scaled down. So the vacuum core, we use our custom glass vacuum chambers, which is something that Inflection developed 10 or 15 years ago. That was really the core of its business. It's this wonderful glass-to-glass bonded vacuum chambers that we are now miniaturizing down to systems the size of the palm of your hand. And similarly, the systems packaging we worked on a lot in this project. So the optical light delivery, the magnetic field delivery, the vibration dampening, the packaging overall, and that's being shrunk as time goes on. And one of the key steps going forwards really is the laser system. So the laser systems that we use were standalone, separate laser systems that were the light was transferred over by optical fiber. But really, these laser systems need to go from being free space and fiber based to chip based. So photonically integrated chips are the future of laser systems, and so you have your laser manipulation and your laser distribution all on chip, and pairing that with the glass vacuum chambers in the top, you can sandwich a photonically integrated chip with a small glass vacuum chamber for light delivery, and this whole system then shrinks down to the size of your hand. So this is the roadmap that we're working towards for a future inertial system. So thank you very much. That's my talk.
Can we see that?
We can see the not the presentation mode.
Get it into presentation.
Try swap displays.
Oh.
Yeah, that's good now.
Okay. Thank you, Keshav, and the last two speakers. I'm Alison Keeley, and I'm going to take us back into the lab looking at. Sorry, what? Okay, yeah, I'm going to take us back and have a look at resilient PNT, focusing on the navigation part of the problem. Keshav gave us a good introduction as to the importance of PNT and the consequences of resilience. I'd like to build on that definition of what is a resilient PNT and talk about the fact that resilience comes in many cases. Some applications may require a navigation solution to be there all the time, but that navigation solution doesn't need to be of the highest accuracy. So we're building up the case for what is resilience in the case of fitness for use of applications. And it's very likely, as identified by the other speakers, that the solution that we're looking for will require multiple technologies if we are going to meet the full requirements of resilient PNT, because what we know today is no single technology, not GPS, not GNSS, or inertial sensors, or any of the alternatives are going to be able to provide all the required information to meet all the instances of resilient PNT. What we have seen historically and traditionally is that resilient navigation has been built around the fusion of multiple sensors. Typically, these were GNSS, INS integrations carried out by an estimator, typically a Kalman filter. And the Kalman filter was there to help us bridge periods of outages. And depending on how good our INS is, it determines how long we can bridge these outages. Now, in certain environments, we're going to have no GPS, and we're relying primarily on an alternative navigation capability. In some environment where we have GPS, the INS is a bridge. But as I just said, it comes down to how good the INS is. So when we talk about inertial sensors, we're talking about a combination of gyroscopes and accelerometers. Typically, 6 degrees of freedom sensors are what we see with classical instruments. And so the slide we're looking at now shows us the range of quantum sensors that are available for navigation. We've heard a lot about cold atom interferometry, and that's one method of generating quantum capabilities for quantum sensing. But in this chart, I'd like to show that there are other techniques for achieving entanglement and building quantum sensors. As we see here, there's things like vapor cells and nitrogen vacancy diamond. And what I'd like to show you in this presentation is how we're using quantum cold atom sensors and nitrogen vacancy diamond to achieve navigation capabilities. So a number of our speakers have already indicated that bandwidth, range, and accuracies are the parameters that we're looking to define when we're talking about quantum sensors. You can see here on the graph, on the table, when we compare classical and quantum sensors doesn't quite have the bandwidth and range as classical sensors, but it has the increased accuracy. They're basically sitting at opposite ends of the sensitivity spectrum. And this is some work that was done with Paul, who spoke earlier, and some of the team, and here are the colleagues listed on this slide. Basically, if we look at a one-dimensional problem over a short period of time, one of the benefits of fusing quantum and classical sensors addresses this so-called phase unwrapping or bandwidth issue to do with classical and quantum sensors. So what we did here was we demonstrated in the graph that you can generate a solution by unwrapping the phase of the quantum measurements, solving the ambiguities in an estimation algorithm, which allows you to enhance the performance. So what we see here is a graph that shows what the position error would be over a period of about 1,000 seconds. And if we fuse the quantum accelerometer with the classical accelerometer and navigate using that, so making some assumptions about a one-dimensional problem with no directional change, we see that we can get a better positioning error. If we extend the timeline over a longer period of time and make some assumptions about the gyroscope that we're going to use in our estimation, and in this case, we made some assumptions about using pretty much one of the best gyroscopes that we could get, and we compared the navigation performance over a period of about 4 hours. And here we can see that with a classical accelerometer, the blue line, that our errors start to drift off. But interestingly, we can see that the same thing happens for our quantum accelerometer when we're using a classical gyroscope. And the reason for this is that if we were to understand the bias and sensor errors inherent in inertial sensors, we can see that the dominant error after about 4 errors is really down to the vertical gyro bias. So even if we were to develop the best accelerometer, but we didn't have a commensurately accurate gyroscope, then we would still be operating in the regime where the gyro bias, the vertical gyro bias, will dominate the solution. In attempting to address some of these problems, we looked at things like within the Kalman filter, what if we were able to use a dynamic model that was better than the standard dynamic models typically used in Kalman filter navigation solutions? In this case, we simulated a trajectory between Sydney and Melbourne and looked at, which is about an hour's worth of trajectory. We had a dynamic model that described the actual aircraft that was traveling between these 2 points. And then we looked at what the impact of that dynamic model would be. And we can see here on the graph that the last red line at the bottom here is really showing that if we have a Kalman filter with a really good dynamic model, we're able to get the best solution. And what this means is that the platform and the platform dynamics is really critical to getting the best out of any fusion approach for quantum and classical sensors. We then extended that idea to look at map aiding. We want to take our quantum and classical inertial sensors and look at maps of gravity signatures across the same region and identify whether the map aiding actually allows us to enhance. So we built in this map matching function, which is typical for a normal navigation solution. So building in the map matching to have a look at what is possible. So we got a gravity map of the same trajectory between Melbourne and Sydney. And then we started looking at what the improvements of using a map matching technique would be. And as you can see in the graph here, we have the two lines that represent what we were seeing before, which is the drift of the accelerometer over time. But what we also see is that by using the map aiding capability, we're able to reduce the error over a period of time. And this is a concept whereby the idea of quantum navigation with maps is emerging as a potential solution to the ability to navigate in environments where we might have no GPS, and we need some sort of aiding solution to help us with managing drifts and biases in our classical systems, which we still need because we need them to support the quantum systems as well. Once we got that system of a quantum, classical INS and map aiding working, we wanted to look then at quantum magnetometers. And in this case, we're looking at quantum magnetometers based on nitrogen vacancy diamond. And what this is giving us is the ability to measure the magnetic field. So as opposed to the last example where we were using a gravitational map, in this case, we're using a total magnetic intensity map and making measurements of the magnetic field with our quantum sensor. And basically the way this map matching technique that we're developing works is that it's based on understanding variability within the map. So areas with high variability, similar to landmark type map matching, areas where you have high variability in the signatures, you're going to get better navigation capabilities than in areas where you don't have this variability and the map matching can't actually distinguish where patterns in magnetic signatures might sit. And so in this example, we simulated a scenario of a constant velocity vehicle traveling again from Melbourne to Sydney. It's over a period of about just over 3 hours. And we have an onboard INS in a GNSS denied environment, and we have an INS in there. And what we can see from this graph, similar to before, we see that our INS only solution drifts off over time. And then we see the solution improved by the map aiding of the magnetic intensity map. And what we're showing here is that if we were able to improve the accuracy of that magnetic sensing, then we're able to even further improve the signal, the solutions we're getting for positioning and navigation. So in conclusion, quantum sensors are poised to change how we do many PNT tasks. But I still think, and I think our other speakers agree, sensor fusion is going to be required to achieve the qualities of resilient PNT. And this includes quantum sensors as well. Map aiding further improves the positioning performance, but there's more work to be done in achieving statistical robustness in that technique. The sensitivity of positioning depends on both map and sensor sensitivity, but ironically, when the sensor surpasses map accuracy, we can actually start generating better maps, which will in turn generate better solutions. So the future work we will focus on will be to integrate the quantum sensors with not just other classical systems, but to look at the architectures in which these sensors are being installed in order to provide this enhanced performance and resilience. So thank you very much.
So Thank you very much to all the speakers. And I think we can open the Q&A session now. We already have multiple questions that have been submitted by audience. So if you have not submitted your question yet, please enter it into either a Q&A box or a chat box. We are monitoring both, and just mark which presenter it is aimed at. So I think all of presenters, if you have not yet, so everyone has turned on the cameras, good. So maybe we can start. I have seen that Paul is very active and he has already answered most, if not all of the questions, but maybe we could read a couple of them anyway for the benefit. But maybe I would start with, let me see, what did I write? There was an interesting question by Leonid, which was not aimed at anyone, but maybe Professor Jürgen could do this one, given all the experiments and projects. So does quantum gravimeter on board the moving vehicle require stabilization, so gyro platform?
I could answer, but maybe this is not my question. It depends how one wants to do his measurements. And I think, yes, you need a certain kind of stabilization, but maybe, I don't know, Keshav can better answer it.
For Keshav, yeah, maybe this was for Keshav, yeah.
So for gravimetry, I guess I can't answer, but for navigation, I'll say that we want to isolate high frequencies so that our system is not subject to high frequencies. But we also, if you perfectly remove all the inertial forces, then you're not measuring anything, and then your quality of your stabilization then is the thing you're measuring. So I think there is a balance between trying to harden your system from external vibration with also trying to make sure you're measuring the inertial quantities of interest at the bandwidth the sensor is interested in. So the tricks here are plotting the the bandwidth response of your sensor, the bandwidth response of the vibration platform, and aligning those appropriately. That's the trick.
Thank you very much. Then we have, maybe we can do one for Paul as well. So Vasilios was asking, do the quantum gravimeters require calibration? If yes, against what are they calibrated? So I know, Paul, you have answered this one, but maybe for everyone's sake, you can say.
Yeah, so I suppose in my answer, it's that these quantum gravimeters, they are absolute devices. So they do obtain the full value of G by referencing a free-falling test mass. And so there's no underlying calibration required.
Okay, thank you very much. Then we have one question for Jürgen from Andrew. Can you do sensor fusion between ground state clocks and grays to get better overall spatial resolution?
So I think basically one could do right now. We do not have so many clock observation, and maybe in future we will have some networks. But I think then we should do it like this in campaigns. So for example, if we install a network on Greenland or in some groundwater change areas, then we could run it. Certainly, as for any data, you can do data fusion, but I think one should at the moment look at it as some add-on, and then it will certainly develop. I think more advantages may be to use ground clocks on tide gauges, because then you have somehow to distinguish between sea level rise and land deformation. And right now you only on land use GNSS. With clocks you have physical heights, and then maybe some you can use it. I think at the moment it is still a little bit more specialized, because clocks have to develop, and we should never forget that we need the connection of from one clock, from observer clock to some stable reference clock or some clock in space. But we have many ideas, and certainly we can also do it in this way.
Yeah. And then we have question for Keshav from Jan Niklas. who congratulates you on the impressive flight trials and asks, could you put into perspective the environmental noise in your trial to the sounding rocket launches of the, I don't know how to read this, -1 and 2 BEC machines that have launched in the past?
Yeah, so I guess I can't speak to the challenges that the -1 and 2 machines had, but just to put into perspective here, during a rocket launch, and maybe this I can talk about the systems in space. There's obviously a real challenge to getting these systems launched. The process of launch is extremely harsh, and that is a really impressive challenge that team has overcome. But during the operation as well, our system has to deal with vibrations. Maybe that's different to orbital based or free fall based systems. So during a level flight, we were flying up to 20,000 feet during our flights. We, as I mentioned, but yeah, with the vibration from the engines is the main thing, and so it's that constant noise source from the engines and also from the airframe that you're dealing with. And so you have a system that is being we were producing a BEC in a pulse scheme, and when we started the flight trials, we were having success rates of the order of 10 or 20%. So 8 out of 10 shots would fail, and we would see a really hot cloud of thermal atoms, and by the end we were above 95% success. So getting that sort of nanokelvin temperatures of atoms stably produced while the environment is shaking around and we're at 273 or whatever, that was really nice. But it's that vibration that's present throughout all of the stages of the process, not just the launch. But we also had to deal with sort of increased vibration during takeoff.
Okay, thank you very much, Kesha. Let me see if we have any more questions. Okay. So
there's
we have
one. There's a long one for
one more
Kisha.
for me.
There's a very long one.
I can go for that. Okay, sure. So in terms of what was the technology based on, so from what I heard from Paul, I believe it's somewhat similar, but I can happy to be corrected. It's a Bose-Einstein condensate based system. In this project, we got as far as producing the Bose-Einstein condensate, splitting that Bose-Einstein condensate into multiple clouds. So I showed an image of a single blob and 3 blobs. What we didn't manage to get to here was demonstrating interferometry during flight. That was something we demonstrated on the ground, but there were some technical challenges there that prevented that. But yes, I believe it's a similar technology. In terms of timing, it was a separate device. It was this optical atomic clock that was brought on board. But all of these systems will be sort of integrated and combined going forwards. And the question about the application, so that was just this project. The application is not simply just aviation, and what we are looking at more nowadays is maritime. So the maritime application is really nice because there is a strong need for resilient PNT in the maritime space, especially maritime defense. Underwater for UUVs, maybe underwater unmanned vehicles, which are doing seabed surveys for wind farms, or they're doing under ice surveys under the Antarctic. I know that was I heard a talk a few weeks ago about that. It's really interesting. And so underwater navigation is a really a good application here, where there is a strong need for a good PNT solution that isn't currently met. And the last question of photonic integration, sort of the circuitry involved. So Inflection are working on a silicon-based platform, but in terms of what we need, we need laser sources that are locked to atomic resonances. So we currently do that obviously separately with macroscopic lasers. We need light amplitude modulation, we need light frequency modulation, and we need light beam delivery into the vacuum chamber. So all of this we need to sort of build into our photonic integrated circuits, and these are being done at the moment inside our company and also worldwide. This is an active area of research.
Thank you, Keshav. So I would like to slowly wrap up. I can certainly say from my side, at least, working in a very noisy environment of urban canyons, that these applications seem to be quite exciting for me and my research. Anyway, so I would like to thank everyone who joins us for today's webinar, especially to our 4 speakers. I hope this is one of the first events such as this, and maybe in future ones we can go deeper into certain issues. if you have any additional questions, please be free to contact our speakers. Anyway, thank you very much for this morning and afternoon or whatever it is where you are at, and have a great rest of the day. So, bye.